Right. I think it's 7 p.m. and I can see more and more people are joining, but because we have a limited amount of time, I'd like to start this session. Hello, everyone. I am Aldeida, and I'm chairing this session today for you. Oh, great. We have our first presenter sharing. Nafisa, that's fantastic to see that you could share your slides. So welcome to this session on software testing. And we have some wonderful presentations here, each of which will last 5 minutes. And the most interesting part then is the discussions. So I'd like to encourage everyone to think about questions that they would like to ask in the second part. Nafisa, we can see your presentation. Fantastic. It's good. Can you test your sound, please, one more time? Can you test it? Okay. Okay. So I can. Nafisa, can you please test it?
Can you see my slides right now?
Yes, we can. We can see.
Okay, Sage.
Great.
Okay, good.
So yes, we have our first presenter, Nafisa, who's going to present on reinforcement learning for test case prioritization. Nafisa, are you ready?
Yes. Hello everyone, I'm Nafisa Kahani, and today I'm going to give a very brief presentation of our paper Reinforcement Learning for Test Case Prioritization that's co-authored by Moshtaba Bagarzadeh, Lionel Bryant, and me. Despite the advantages of using CI, there are some challenges with using CI as well, especially when it comes to regression testing, which is affected by the dynamic environment and time constraints of CI. The simplest way to do regression testing is to run all the previously defined test cases. That's very time consuming and expensive, especially for very large systems. There are a number of methods such as test case selection and prioritization to follow to solve this problem. Test case prioritization is used for finding the optimal order for test case executions in order to detect faults as soon as possible, where we give high priority to test cases if they are more likely to fail and also they have less execution times. There are some ways to apply test case prioritization to CI, such as static and dynamic analysis, heuristics, and machine learning. That our work is focused on machine learning techniques, especially reinforcement learning or RL techniques. Reinforcement learning or RL has recently been applied to challenging scenarios which require continuous adoption. And also we have many advanced RL algorithms proposed over the last few years. So to formalize the action and state space of RL, we use ranking models, including listwise, pairwise, and pointwise in our paper. So in our paper for listwise, we use a list of test cases as a state, and the RL agent return the rank of all test cases here as a as a vector of discrete values. Then we calculated the reward based on the differences between the assigned ranks and optimal rank, where a smaller distance means higher rewards. In pairwise ranking, an agent is given with a pair of test cases, something like here. And based on the and then we use the sorting algorithms. And based on the optimal ranking, the reward was calculated for test cases with different verdicts. Assigning a lower rank to a failed test case results in higher reward. Otherwise, assigning a lower rank to a test case with shorter execution time results in a small reward. And then in point-wise ranking, at each step, we consider only one test case, something like here as a state, and then the agent returns a real number that corresponds to the ranks of the test case. The reward was also calculated based on the difference between the normalized optimal ranking and assigned rank. And then to evaluate the algorithms, we used 10 RL algorithms that are provided by the stable baseline framework. And we ran extensive experiments on two categories of data sets, including simple history data and enriched history data, that both of them are publicly available. And regarding the results in terms of accuracy, pairwise performs better than pointwise and listwise. And in terms of training, listwise performs worse than pointwise and pairwise. And we also examine how the best configuration of RL performs compared to the state-of-the-art ranking models. And our results show that MART had the best results among ML-based solutions, and also our best configuration significantly improves our ranking accuracy over that of MART. So based on our results, we noticed that relying on test execution history doesn't provide sufficient features for learning an accurate test case prioritization policy. And also, and regardless of the ranking model and RL algorithm, also using data sets with sufficient features, then RL has the potential to be a reliable and adaptive solution for test case prioritization in CI environments. Thank you.
Thank you, Nafzeh. Let's go to the next second presentation, which is on building system-aware multi-language regression test selection in continuous integration. Thanks, Daniel.
All right, I hope you can see the screen.
Yeah.
My name is Daniel, and I'm going to present our work, which was done in collaboration with IVU Traffic Technologies, which is one of the world's leading providers in software for traffic providers. So let me give you a summary, and if you're interested in the details, have a look at the paper and then at the presentation that I pre-recorded. So the context that we're looking at is at IVU Traffic Technologies, and developers there create pull requests to release branches regularly. And before they are allowed to merge these pull requests, CI pipelines are run. And they look roughly like this. So you can see already there are two parts of the code base, one C++ code base, and then one Java base. And before we were doing this work on test selection, we had significant testing effort and execution effort for building the code base, running static analysis, as you can see here in the second Java step, and also testing, running short-running tests and long-running tests. And the effort was simply too high to run it every time you have a new pull request, and you have to wait until all these tests have been executed. And then we looked into existing safe RTS techniques and found that they are impractical. And why safe RTS in this case? So why can't we simply rely on heuristics as in the presentation that we just saw? Well, all these changes are going into release branches, and they could potentially go into customers' code bases. So we need something that actually finds all the failures related to the changes introduced in the pull request. We can't simply rely on heuristics or some statistical model. And what we found on the existing techniques is they are impractical in this context because first, they require a full build of the code base. They usually rely on some kind of checksumming algorithm. So you have the checksum of the version before the change and then the version which contains the change, and you want to compare these checksums, and that requires the code to be built. But in this case, building already takes significant effort and significant time. So we want some kind of selective build included there as well. So we have to do the selection before we compile the code base. And the second part was that we have a really multilingual code base here. We have a lot of cross-language links using the Java native interface. And also we use a lot of different domain-specific languages such as XML and also CSV as expected test results. And these techniques were not feasible in this case. So our proposed solution is a build system aware multi-language RTS technique, which is based on language agnostic system call tracing. So we try to identify which files are being touched by an executing test. And then using these file level test traces, we select tests that are affected by the changes introduced in the pull request. So looking at the outcome, we can see that we introduced a new step here in the CI pipelines. This is our RTS technique. And what we can see here, it has two outputs. It has once the selected module, so which code modules have to be built and analyzed. And then secondly, we have the selected tests that need to be executed. And we conducted a case study on the time period of 5 weeks at IFAU. And we found that the test duration reduction is on average 42 to 72%. It depends on the how old the branch is we evaluated on. We did not miss any real failures. There were some flaky failures, but we see that there is some conceptual unsafety that could potentially be introduced. So for example, if we have outdated test traces. And for the end-to-end pipeline reduction, we found that we can save 50 to 63% of the pipeline time for pull requests on average. Thank you very much.
Thank you, Daniel. And I can see questions are coming in the chat, so please keep putting your questions there, and I'll read them at the end when all presentations have finished and we can discuss them. So the third presentation is Testing Machine Learning Systems in Industry, an Empirical Study. Can you unmute yourself, Shuya, please? Yeah.
So yeah, this is Shuya Li from Jiaotong University, and I will share one work of my team. It is an empirical study on testing the machine learning systems. So first, I guess most of us are familiar with the machine learning software systems, no matter in research or in our daily lives. In general, these systems have some new properties which do not exist in most traditional software systems. For example, their behaviors can be statistical and determined by data. So we naturally wonder, how does the machine learning incorporations affect the software testing process? For example, we usually don't have test oracles in machine learning systems, and the test results of machine learning models sometimes cannot be reproduced. But despite all these problems, the industry has developed some successful machine learning applications. So it is natural for us to absorb some inspirations from the industry. And to the best of our knowledge, the testing problem on machine learning systems has not been well studied from this perspective. So in this paper, we conducted a study to investigate how the practitioners test their machine learning systems, especially their testing activities, their good practices, and so on. Our methodology is based on interviews and surveys among these practitioners. First, we interviewed 7 senior practitioners from United States and China, both are the big companies. And in these interviews, we carefully investigated their concerns, practices, and the challenges on major testing activities. And then we designed a questionnaire and distributed it to practitioners to verify our findings in the interviews. We received responses from various product areas. So with these interviews and surveys, we organized our results of the study by 3 major testing activities, which is test data collection, test execution, and test result analysis. Due to the time limit, I only introduce several interesting findings here. So first, we noticed that most research work on machine learning testing are focused on test case generation for machine learning models. But in our study, we find that none of our interviewees have adopted these techniques proposed in research. And the major reason is that existing techniques are all based on seed inputs and then mutate the seeds to generate more test cases. But for developers, even collecting a seed corpus is expensive. So in other words, their pain point has not been addressed yet. This is an open challenge and could be a good research opportunity. And secondly, in machine learning systems, there is entanglement among data, model, and source code, which makes the testing process less efficient. Although we can test each component individually, they are entangled internally, so any changes in the system can mean to retest all components. And moreover, in our survey, we find that there are different architectures of machine learning systems. I show here that the hierarchical system divides a problem into some sub-problems and solve each sub-problem with multiple models. And our respondents find that testing this kind of system could be even harder. This may also be a research opportunity. Yeah. And finally, we need to conduct a test result analysis. And in practice, the quantitative analysis is based on evaluation metrics such as accuracy, recall, and so on. And most respondents in our survey agree that designing the metrics for machine learning models is a sophisticated task. Actually, there is no consensus on which metric is the best because the models are statistical or even uninterpretable. And there are so many properties to test. So we also received many open questions in this part. For example, for a hierarchical system I just mentioned, how to aggregate the metrics on each part to evaluate the whole system. So to conclude, we find out some important implications from the industry for machine learning testing, and we hope this work could provide more insights and make researchers better positioned to help practitioners on machine learning testing. Yeah, that's all for my talk. Thank you.
Thank you, Shuya. Very interesting talk. Next, and I can see more and more questions are coming, which is great. Next question is GiftDroid, automated replay of visual bug reports for Android apps. And we have Sidong that is presenting. Thanks, Sidong.
Okay, can you see my screen?
Yes, and we can hear you.
Okay, cool. Hello, everyone. My name is Sidong from Monash University. I will present our work, GiftDroid, automated replay of visual bug reports for Android apps. First, I would like to briefly recap the motivation of our work. Bug reports are virtual for software maintenance that allow users to inform developers of the problems encountered. However, writing a clear and concise bug report takes time, especially for non-developer or non-testers who do not have that expertise and are not willing to spend that much effort. And a poorly written report will be even poorly interpreted. Compared to write it down with instructions, video-based bug reports lower the bar for documenting the bug. First, it is easy to record the screen as there are many tools available. And second, video recording can include more detail and context such as configurations and parameters. Despite the benefits of the video-based bug report, it still requires developers to manually check each frame in the video and repeat it in their environment. We find that the bug recording of a large number of frames and vary resolution make it difficult for developers to replay them in their setting. And also, as an important information to show users' actions, some recordings contain touch indicator. However, we find that there are only few recordings enabling the touch indicator, make developers have to guess and try the potential actions to trigger the target page. Therefore, we are motivated to develop an approach to automatically replay the recordings for developers and testers. Our approach consists of three main phases: keyframe location, GUI mapping, and execution trace generation. That is it, given an import bug recording, we first localize a sequence of keyframes and subsequently map them to the existing GUI transition graph to extract the execution trace. Next, I'd like to briefly introduce each phrase. For the first phrase, the goal is to identify keyframes, set the states in which GUI are fully rendered. To achieve that, we leverage the image processing technique to build a similarity score for consecutive frame comparison. By observing the frame sequence, we annotate the keyframes from the recording if the GUI is in a state. That is, the consecutive frames are similar for relatively long duration. Then we map each located keyframe to the GUIs in the GUI transition graph. A GUI transition graph is widely used to illustrate the transition across different GUIs triggered by typical elements. To map the keyframes to the states in the graph, it is a well-known image searching task. We adopt feature extraction method to compute the similarity score and map the keyframe to the most similar GUIs. After mapping all the keyframes, we obtain an index sequence in the graph. Finally, we utilize the index sequence to detect an optimal replayable execution trace. However, we face two challenging problems. One is the previous approach for keyframe location and GUI mapping may not be 100% accurate. And the other one is the recording may start from any states in the application. To overcome the issues, we propose an algorithm to address the defective sequence in previous phrase and complement the missing states between application launch and the first keyframe in the recording. In detail, we first find all the sequence between application launch states to the last index state, and then select the sequence that has the longest common subsequence as the execution trace. In summary, the visual bug recording is training in bug reports due to its easy creation and rich information. To help developers automatically reproduce those bugs, we propose GIFDroid, an image processing approach to convert the recording to executable trace to trigger the bug in the Android apps. And in the future, we will keep improving our approach for better performance. And thank you very much.
Thank you, Sidong. And the next presentation is Build Sheriff, Change-Aware Test Failure Triage for Continuous Integration Builds. We have Chen here.
Okay. Hi everyone, I'm Chen Zhang, come from Funan University. The paper I will report is Build Sheriff, Change-Aware Test Failure Triage for Continuous Integration Builds. First, let me explain what is CI, that is continuous integration. Previously, present have explained the related concepts. CI is a software development practice that requires people to frequently compare, static, analyze, test, and integrate code changes. CI has been widely used because it can automate build process, detect errors earlier, and reduce risks in software development. Why we do this research? CI builds often break, and test failures are one of the most common reasons for broken builds in CI. According to a recent study, they are responsible for 59% of broken builds. Developers need to manually localize and repair the underlying faults. However, it's not easy for them to analyze test failures in a build because a build is not always triggered for every commit, and the build may change multiple source code files. In that sense, it's expensive to diagnose all techniques are designed to cluster test failures that are caused by the same fault into the same cluster. In this way, test failure diagnosis can be realized by only analyzing one test failure in each cluster, but not all the test failures, which can reduce manual diagnosis cost. Test failure have two types. If a test throws an exception when running, we call it an exception failure. If the actual outcome of the test differs from its oracle, we call it assertion failure. Here is an example exception failure. This test throws an IO exception. Here is an example of assertion failure. The actual message is different from the expecting message. We first present a large-scale empirical study to understand test failures in CI builds, and found that both exception and assertion failures are common to cause test failure builds. Therefore, test failure triage in CI should support both of them. Multiple test failures are common in CI builds, which represents the potential reduction of test failure diagnosis cost that can be achieved by test failure triage. Test failures in a large part of the test failure build have only one root cause. Thus, test failure triage in CI should be aware of this specific characteristic. Then we propose a new change-aware approach to triage test failures for CI builds, so that test failures with the same root cause are put in the same cluster. It works in 3 steps: triage knowledge preparation, exception failure triage, and assertion failure triage. It first prepares triage knowledge by analyzing the build log, the project source code, and the code changes from previous past build. Based on the triage knowledge, it then uses different strategies to triage exception failures and assertion failures. We develop a pipeline of 3 strategies based on complexity of code changes, change-aware stack tree similarity, and exception message similarity for exception failure triage, and a pipeline of 2 strategies based on complexity of code changes and change-aware test code similarity for assertion failure triage. The 4 research questions to evaluate the effectiveness and efficiency of build sheriff. In summary, this paper makes the following contributions. We conducted a large-scale empirical study to characterize test failures in real-world job projects and motivate test failure triage. We propose a new change-aware approach, build sheriff, to triage test failures in CI builds effectively and practically. We conducted experiments on 2,200 broken builds to demonstrate the effectiveness and efficiency of build sheriff. Thank you. That's all.
You're muted. Sorry, you're muted.
Maybe you didn't open your mic.
Yeah.
Thank you. All right. So the last presentation, and then we will we'll go through the questions. We have natural attack for pre-trained models of code, and we have Joel here that's presenting.
Okay. Can you see my screen?
Yes.
Okay. Cool. Hi everyone. The paper is titled "Natural Attack for Pre-trained Models." Student from Singapore University. There are many research work being done to use AI models for solving software engineering tasks. these models of code are not robust enough. On the example illustrated by the left figure, a model can correctly classify the input, but if the variable A is renamed to something else, it will be wrongly recognized by the same model, even though the program behavior is exactly the same. The fact that semantic preserving transformations on code can change model outputs highlights some security threats. Assuming there is a malicious attacker or programmer in a company, and the company deploys an AI system to conduct several software engineering tasks, like detecting the defective code. The attacker wants to cause some negative impacts on the code base, for example, merging buggy code into a repository. Anyway, just negative impacts. To avoiding being detected by the model, the attacker uses some semantic preserving transformations without modifying the function of his code to create adversarial examples. The model of the code are usually deployed in the server where the attacker cannot access the white box information like the model parameters. So in this paper, we assume a black box attack setting. However, software development is still a human-in-the-loop activity. Code review is widely adopted as one of the best practices. If we look at the adversarial examples on the left side, changing LM to uphack digits or music service is actually not natural. They are very likely to be treated as bad identifier names, and such obviously unnatural adversarial examples might be able to fool the model, but can be rejected by the human. So we suggest that the adversarial example for modeled code should consider two requirements. On the one side, it should be program semantic preserving. It cannot change the program behavior. On the other side, it should be also natural to human judges. We quoted one statement from a project that says that software, as written, has two audiences, the machines that run it and the humans who maintain it. This, to some extent, inspires our study, and we also find some very good papers sharing the similar opinion in ECLID 2022. We use a mask language prediction function from the pre-trained model of the code to generate natural substitutes for variables. We feed the left text, I have a thing, which is hard to solve, okay, into the codebird, which predicts the mask tokens as a problem and bug, and another problem capitalized with, first character being capitalized. The results are natural as a problem and bug can be hard to solve. It means that the mask language modeling can predict words that can fit into the context. The above example motivates us to use the mask language prediction to generate natural substitutes for identifiers in the code snippets. For example, an original identifier is a prop, and the codebird can predict a natural replacement property, which can describe the type of this variable. We extract all the local variables from the code snippet and generate a list of candidates for each variable using the mask language prediction. Beyond that, we also re-rank the candidate list. We use each candidate to replace the original identifier and feed them into the model. But this time, we compute the embedding of each token rather than predict the masked tokens. Then we compute the similarity between the original token and the new identifier and select the top 30 candidates with the highest similarity. We propose a two-stage method to generate adversarial examples. The first step is to a greedy algorithm to find these examples fast, and the second one is based on a genetic algorithm, which is applied to do a more comprehensive search if the former one fails. But due to the limited time, we refer interested audience to full presentation or the paper for more details. We choose two state-of-the-art pre-trained models as our victim models and evaluate the three important tasks, including vulnerability detection, clone detection, and authorship attribution. We conduct a user study to analyze the naturalness of examples generated by our method, another method MHM, and another one MHM-NES. So the participants were asked to give a score on a 5-point Likert scale, deciding whether they think the new variable looks more natural. 1 means strongly disagree, and 5 means strongly agree. We plotted the average score in the figure, and the results show that the participants consistently think that adversarial examples generated by our methods are more natural. We use 3 metrics to measure the performance of an adversarial generation method: attack success rate, variable change rate, number of queries to the victim model. We can observe that the simple greedy attack, the first step, can already outperform the Pyro state-of-the-art baseline. Using the genetic algorithm can boost the results even further. On all victim models, our method modifies fewer and queries the victim models less than the baseline does, showing that our method is more scalable and make less changes. We leverage the attack, also work on the training data. Then the general examples are then augmented into the original training combined set. So from this table, we can observe that the adversarial examples generated are valuable in improving the robustness of victim models. So in the future, we also plan to extend the attack to other models or other different types of semantic preserving transformations, we also plan to develop the robust pre-trained models rather than just getting robustness by fine-tuning each model again and again. Okay, that's my presentation. Thanks. You're muted again. Sorry.
Why do I do that? Thank you. Great presentations, everyone, and great work. So now in this second part, we will go through questions, and I can see questions in the chat, and some of them have already been answered, but I will go through them. So as you know, people might watch this video later on, so that and you might have additional things to add to those questions. But also, I'd like to encourage the audience, if you want to ask questions, please unmute yourself and ask your question. So I'll first go through some of the questions in the chat, and then I'll come to the audience. We have a first question from Zhou, and talking about Zhou, did you want to ask that question you've written in the chat? Do you evaluate the agent on real systems? That was meant for Nafisa for the first presentation, which which was about reinforcement learning for test case prioritization. So it's a question about, Yeah,
I can talk about it later. Sorry, a bit more. So I understand that the data are from the real systems, but what I mean is when you are testing your agent, your model, you are using them to really select some test cases and really execute them, or you also use some historical data to evaluate them.
And Nafisa, this question is for you. If you can unmute yourself.
Yes, we use the historical data.
Okay. Yeah, no
Yes,
problem.
But as I mentioned, our data sets were collected from a CI for a real system. But we tested on historical data from the previous test case execution.
Okay. So another question related to this. So you test your agent within this project, right? So you cannot transfer one project. Agent train on one project to another. You must test it within the project, right?
Yes.
Okay. Thank you.
Yeah, thank you.
Thanks, Joe. And we have a question from Daniel. Again, did you compare simple heuristics? And a follow-up question. I don't. Did you want to summarize your questions, Daniel, to Nafisa?
Sure. I think we already answered all of them in the chat, but the question was that whether they compared simple heuristics as well, such as historical failure frequency for prioritizing or ranking the tests. And she said that they did some follow-up work which compares the ML-based or the reinforcement learning-based techniques against heuristics.
Yeah.
And then there was another question for me regarding calculating the code features and the cost related to that, because they, I think, use some static code analysis, like calculating object-oriented metrics and complexity metrics, and you usually require some kind of AST representation to calculate these features, and that can be costly. So I was wondering what the cost is and whether they incorporated that, and then she said they also considered that in some follow-up work, and also posted the preprint there.
Okay, great. Thanks, Daniel, for summarizing both questions and answers. That's great. We have a question for Shuye from Zhou. So that is what kind of AI systems you focus on in your survey? CV, NLP, audio-based, etc.
Yeah, actually, we focus on various kinds of deep neural networks, and it includes CV, NLP, and speech. Yeah, and also the some ranking systems like the recommendation systems or the search engines. Yeah, I think these are the most mainstream machine learning systems in industry. So we focus on these kinds. Yeah.
Yeah, I mean, if do the do developers of different systems like have different preference in terms of software testing, machine learning testing? Because I think in software engineering, people focus more on CV or classification, but for the others, it's a bit less, like reinforcement learning or audio. So do they have?
Of course, there's actually some major differences among these different kinds of systems. It majorly depends on their type of task. For example, for a classification task, they have some testing techniques, especially for this classifications, right? And for the ranking system, the testing may be more difficult because they have lots of candidates, and they actually is more difficult to evaluate whether the ranking results are good or not. So they may take more human efforts to evaluate these kind of systems. Yeah, it's also difficult for testing. So yeah.
Okay, thanks.
I think, yeah.
Thanks, Zhou and Shuye. Shuye, there's another question for you from Daniel. How do you envisage regression reduction? What's the difference to increasing model robustness?
Yeah, I think it's a really good question. Actually, recently I'm doing a work about regression reduction on deep neural networks models, and we actually find that the regression problems on the DNN models is actually very similar to the robustness. Yeah, for example, when we enhance the model or improve its robustness, the regression sometimes can be decreased also. But we actually find that there's some major differences. And one of the most important thing is the scenario of the regression. For example, there are so many different scenarios or changes of the system that can cause the regressions on DNN models. For example, different randomness, or when you add some new data, for example, the data of a new class or some data you aim to augment the system, this can all cause the regressions. And with different scenarios, the regression problems have some different characteristics. So it may be more complicated than the robustness problem. Yeah.
A follow-up question?
Great, thanks for that. So,
can I ask a follow-up question?
Yeah, sure.
Okay.
Yeah.
So I'm wondering, how do you select the test cases or how do you define the regression test cases? When do you say, well, this should be a regression test case that should be used for future versions of the model?
Yeah. We actually now on DNN models, the regression testing is still conducted by retesting all test cases, which means that when we for these models, whether we update it or when the model evolves, we actually have a test data set for our models, and we may update our test data set from time to time, but in regression testing, we actually need to retest on all the test cases in the data set. So, yeah. We haven't, it's still an open question to select or prioritize the test cases for deep models. Yeah.
And then you consider it a regression if any of the labeled data points inside your regression test set has a wrong classification?
Yeah.
Okay. Thanks.
Thanks, Shuye. So one more question in the chat, and then I'll ask the audience in general if they want to ask any additional questions. So this is to Chen. What do you think? So from Daniel, what do you think? To what degree do your findings transfer to non-Java projects?
Okay. The dataset we used is all Java projects, and our approach is designed for Java project. In our approach, we use several strategies such as symmetric similarity, test code similarity. I think as long as the other programming language project contains that have such information, we can apply our approach to them. Also, of course, some engineering effort is needed to extend our approach to support other programming languages.
Okay, thanks. Thank you, Chen. So let me ask, I wasn't sure if the audience can put their questions in the chat, so I'd like to ask everyone if they have any questions they'd like to ask to our presenters. Maybe. Let me see. I don't see any. So you can just unmute yourself and ask directly to any of our presenters. I guess since we don't have anything at the moment, I might go to my questions then, which I left them. But of course, please feel free to unmute yourself at any time if you can. I'm not sure if you can see the chat. You probably can, so you can put your question there too. Okay, so
another question.
Oh, good.
Sorry.
Yeah, Daniel, go ahead.
Yes?
Please.
Okay, sorry. So Nafise, you see, I find this very interesting because I've worked on a similar topic before, and I'm curious. What do you think? How much white box analysis, like the one that you're doing with static analysis, and I briefly looked at the paper that you provided regarding dynamic analysis, how much information beyond metadata, like historical failures, do you think your models need to actually have a significant benefit? Do we need the static and dynamic analysis, or can we simply rely on the metadata? Because we only look at metadata because there are a lot of environments where you're limited to metadata. You cannot use any language-specific static or dynamic program analysis. So I'm wondering, what's your take on this?
Metadata information for sure is not enough, and we should include the static and dynamic analysis. And actually, that was one of the findings for this work. And in our research that I share with you, we collect a comprehensive set of features that we should consider when we want to, use for machine learning based test case prioritization. And in that work, we consider both static and dynamic. Consider the full set of features.
Okay, so you would say it's required. And what if you're in an environment where you don't have that kind of information and it's not easily obtainable? What would you say are the most relevant features then that you would still need to have?
In that case, we should use the historical data information when we don't have access. But for historical data is not enough.
Okay, thanks.
Thanks for that. Okay, so I had a question for you, Daniel, actually, which is about, your, I was curious about the industrial case study that you used. Can you tell us, I know the presentation was 5 minutes, so I was curious to know a bit more about it. How did you go about selecting, how big it was, and what were the features of this case study?
Yes. So the code base that we're talking about at IFAU has roughly 13 million lines of code. It's a monolithic code base. And as I said, it's basically split into two parts, C++ and Java. And they test a lot of both code bases, obviously. But we considered the Java code base specifically in this study. And we try to reduce the amount of effort for building, for analyzing the code, and also for testing. And there are some tests that only run inside the Java code base. And then there are a lot of tests that actually have use the Java native interface to use some dynamically linked libraries that are built from the C++ code base throughout their testing process. So they load the DLLs in the beginning, and then they execute a lot of C++ code, and then they go back and execute a lot of Java code. And these kind of tests are specifically hard to get if you have changes to the C++ code base, and you need to figure out which Java tests to execute. So this is the multi-language aspects that are really relevant in this case. And maybe a little bit more context on the industrial case study. So we've deployed this test selection and selective build to all of the release branches. They have 10 release branches, and we have rolled out that to every single release branch. It's been in use since September. And as I said, we have these end-to-end pipeline savings of 50 to 63%, which the developers really like, and they would not want to miss that. And we're currently expanding that a bit also towards the C++ code base, because currently we're focusing on Java tests. And also we have some problems with imprecision in our test traces, but you can read that in the paper. That's very detailed now. And so we're trying to expand that to the C++ code base. And also, because what we're looking at now is mainly the continuous integration environment, we're also looking into pre-submit testing and try to use the information that we already obtain for every test case, try to use that also in the local development environment, so that you have these benefits also when you are developing something locally and you want to figure out which tests to run.
Great. Thanks for that very comprehensive answer. That sounds like a very challenging problem, but yeah, that's great. I had a question for Zhou on the natural attack for pre-trained models of code, and I was curious when you were talking about, you know, the you asked some humans on looking at these adversarial examples and rating them whether they were natural adversarial examples. I was curious to know, you know, what is a natural adversarial example? I know you showed the property, but how would you rate, I guess, a natural adversarial example? What would they be looking for?
So basically, we present them to two examples. So they don't know whether it is the original or one generated by any of the methods. Then we highlight the variable, and we just ask them which one do you think can fit the context better or capture the semantic meaning. Now, what do you think it should be here? And evaluate whether this variable here fits or not. Then and we do give them some examples about the natural ones and unnatural ones, and they use the whole guideline to make their decisions.
Okay, now that was interesting. That I guess I was also thinking, since it's adversarial, will they also be looking at the severity of, you know, the impact of that exam, not just whether it's natural, but also whether it's indeed adversarial. So they were only looking at the natural part, right?
Yes, because what we do, we don't change the program behavior. So the adversarial, the term, just make the results, means it change the behavior of it change the output of the model. So that's what the adversarial mean. But we wanted to do it in a natural way. So here, natural just means whether it looks good to human eyes.
Yeah. Okay, makes sense. Thanks for that. That makes great, and it's very interesting research. So one question that I had about you know, the presentation on testing machine learning systems in industry, an empirical study by Xu Yue, which was quite fascinating, that now we have some evidence from, you know, we have some evidence on what industry does in this space, which is a much needed evidence. And I was wondering, Xu Yue, and I haven't read your paper, so maybe it is there or maybe it's not. do these developers, what kind of metrics do they care about coverage? I mean, we talk a lot about coverage in testing. How do they consider it? Or you talked about some metrics, but I wasn't like, what kind of measures do they use for estimating how good they've tested these machine learning systems?
Yeah, okay. Yeah, I just, the metrics I mentioned just included, their evaluation metrics for model performance, such as the accuracy, recall, and so on. As for the evaluation of the whole test process, like the coverage, I think the industry hasn't gone this far. Yeah, it's still very big open challenge for them to evaluate to what extent their testing process has been. Actually, I'm aware that there's many related research work on test coverage for deep neural models, right? But it actually hasn't been adopted in industry or in practice because, the models is still not interpretable, and sometimes the testing results are not reproducible. So that's in practice, these are the major or the problems for now. So I think we still have some long way to go. Yeah.
Great, thanks, Xue. And I have a final question for the paper on Gidroid, the automated replay of visual bug reports for Android apps. It's quite interesting paper, and I was wondering, you talked about, I think, that I believe you use human annotators and, artificial recordings. Can you tell me a bit more about these artificial recordings and how they were generated? I hope I haven't misunderstood your work.
Okay. So basically, we focus on the general recording from the GitHub. So normally users post issues, and they don't want to spend too much effort to writing some very detailed description on how to what's the step and what's the environment, kind of that stuff. And also, there's a gap between the developers and the users about the bug replay. Like user may not pay attention on like the parameters or some of the small settings, but when the developers replay the bugs, they probably focus on this kind of small settings. So the bug recording becomes a trend right now. I think there's tools like embed in the GitHub that allows users to record the bugs. However, this kind of the recording is general, and it might captured like in the own device and own settings. For example, like using varied resolution, and many have the captured in different frame per seconds. So our work is going to focus on that kind of the artificial visual recording and help to replace by the execution trace. Yeah.
Okay, great. Thanks, Xidong. And I do have many more questions, but we're running out of time. So I'd like to thank our presenters for the wonderful presentations, and please have a look at their papers, which you have a preprint in the program. I'm attaching a link here as well, which somehow didn't work. It changed it to emoji, but you have the whole program together with preprints in the ICSA conference website. And I'd like to thank our audience for attending, and I wish you enjoy the rest of the program at ICSA, and see you in the next sessions. Bye, everyone.
Thank you. Bye.